All right, again, for some reason it put the alpha lock on. I have no idea why, but you can just hit alpha to turn that off. I put the relevant data for 2005 into L2, and each one of those values occurs once. So I'm going to change, so I hit alpha again to turn the alpha lock off, and I hit the number 1. Instead of hitting the number 1, just leave it clear. Because apparently the number 1 is not a frequency list. And the calculator, for some reason, in this one moment, is deciding to be overly literal. All right. So I'll write that out again. It is here. Not a frequency table. Might as well cut that in for consistency. All right, so go to calculate, and this is the summary statistics. So let's get all this information out of here. Copy and paste it, and again, I'll refresh your memories on what all this stuff means. Remember, the down arrow means that there's more information to follow if you hit the down arrow. So hit the down arrow, and keep going until the down arrow becomes an up arrow. All right, so this is all our 2005 stuff. So we have the mean. The mean and the standard deviation should be obvious. But if it wasn't before, maybe now it is. X bar stands for the sample mean. And that is approximately 47.968. The SX stands for sample standard deviation. And that's approximately about 44.393. I should use approximate for the mean also. We'll have to do something with that in a sec, but for now we'll just deal with it as is. All right. We don't need this, this, or this for now. Okay. They have their uses, but not for this. Okay. So these two guys are important. I think this stuff here requires no explanation because that's what we need for our 5-number summary. So we have all the stuff that we need for our box plot. So I'm going to make a note that they should be 2, 13, 24, 17, 9, and 165. All right. So now what I want to do is create a number line. Do not have a double-sided. So let me remedy that forthwith. Line style should be solid, just like my teaching skills. Just solid. All right, so what I want is a convenient value that's lower than my minimum and a convenient value that's larger than my maximum. So kind of like what we did with our frequency histogram. So we'll go from 0 to 200, break it up into even increments, so you can establish a nice scale. I think 25s will be okay. 25, 50, 75, 25, 50, 75. All right. Just give me a few benchmarks along your number line, and I'm happy. I need to be able to determine what your scale is. Otherwise, you can't get full credit. Okay? Because this is what people do. They say, I'm reading minds now, based on what I see on paper. All right. I don't know how to come up with the numbers for the box plot, but I know what it's supposed to look like. So, all right, I'm just going to put some numbers down. And then, all right. And, yeah, all right, next question. It's like, well, that's a box plot, sure. It's a good looking one, I'll give you that. But it's not necessarily the box plot for this particular question. And also something else that people do is they'll just draw a generic box plot and then they'll label it 2, 13, 79, I missed one, 24, 79, and 165. They'll do that. This is completely wrong. All right. The idea is not to draw some generic box plot and label it with numbers. The idea is to see where the numbers fall on a numerical scale and how the box would look when it's placed appropriately, all right, and what kind of information that gives us about the distribution. So this is important. Now I can estimate, though, because 2 is like, right, yeah, we got 13. I mean, it's like barely a smidge sort of right of 2. 24 is like, meh. 79 is like, meh. And then we have 165 all the way over meh. So that's giving us a truer representation of the distribution of the data. Now, it's a complete crap drawing on my part, but it still gives us a sense of where most of the data exist. And that's really what we're looking for. I mean, a perfect, or not a perfect, nothing's perfect, but a much better, a truer, the truest representation of the data would be computer generated. Right? So getting it on paper, I mean, you'd have to have a really steady hand, a ruler, and a lot of patience. And some of us will, I mean, I'll grade them and I'll look at that and say, that's even better than what a computer would produce. Great job. But for the most part, it's just some slapped together graph to get a sense of what the data looks like. Right? And that's what we're looking for. Shockingly. We're not looking for the picture perfect rendering. We're looking for the gist of the data, the shape of the data. Right? If your graph gets that idea across while being appropriately labeled, then you've done your part. All right? Everything else is left to computers. All right, we'll get to number 4 in a minute, but that's all there is for number 3. You can label the benchmarks if you want, but I've labeled it on the side, so I did my part there. All right, so everything that we need here is taken care of. If your number line is some funky scale, then make a note of that. But I don't need units. I don't need like meters or anything like that. That's all represented in the raw data. All right, now number 3 is really just skill-based. It's kind of like a way for you to just kind of check a box and say, I know how to do this. All right, so same process that we used for the previous question, except now we're looking at L1 because it's the year 1970. All right, so data's already in, stat, calc, option 1,
I'm going to turn off my alpha so I don't get confused. And then just select second 1. I'll snip that in. I don't think I could state this part often enough, so I'm just going to say it over and over and over again, because it's such a common question. How'd you know to do L1 here, but L2 for the last one? Because that's where the data is. All right. Because that's what heroes did. Reference? All right, so you didn't watch any movies from the 1970s and also last year. First one was Blazing Saddles. This one was Thor Ragnarok. Can't handle movie, I'll start doing historical. That'll make you feel really bad. Because then it'll be like, oh, I should know this. Anyway, so mean, median, range, and standard deviation, all things you get directly from the calculator. So I hesitated on range because you get it directly, but there's still a small calculation you need to do. The other ones you directly get it. It's in this list somewhere. All right, you just have to flesh out where it is. So again, this is for 1970. The mean is 90.323 approximately. The median, 83. The mode, you're out of luck. You got to figure that out on your own. The range by definition is max minus min. So depending on the nature of the data, that might be harder to come by. In this case, it's not bad because it's just 206 minus 13, which is what, $1.93. Mid-range we'll come back to. Variance we'll come back to. Standard deviation, we talked about that. That's the SX 51.156. So, mode. You gotta come up with that visually. Visually could mean one of two things. It could mean with the raw data. I mean, it always means with your eyes, so I'm not going anywhere with that. But with the raw data or with the graph. Graphs have their place. I mean, you can do something with it, but it's not always the most appealing way to go about it. If you can pick it up right by looking at the data set, that's the best way to go. So look for any, and since the data are organized in increasing order, if there are repeated values, you should be able to pick it out. 45 occurs twice, 55 occurs twice. Does anything beat twice? No. 145 also twice. So 45, 55, and 145. The other way to do it would be to create a histogram that went by single numbers. All right, so with an X scale of 1, depending on how many times a number occurs, that could be a pain. But in this case, since the most frequent number only occurs twice, it might not be the worst thing in the world. So the data are found in L1. So if you wanted to go this route, if you're a calculator savvy kind of person and you kind of gravitate towards the calculator way of doing things, then this might be for you. So second, y equals. We're looking at list 1, because it's still a histogram. So I would change L2 to L1. And you know what? Even if you don't want to do this problem this way, you may want to change it back to L1 anyway, because who's to say that the next time you do a problem, you're going to want to do a graph of L2. So I would change it back to L1, even if you don't plan on doing this problem this way. All right. You could do the zoom 9. It'll give you a histogram. That histogram is based on intervals. So if you hit trace, it's going from 13 to like 45. I don't want that. What I want in my window is to go by ones. And then hit graph again. Okay. That did not work. Why would that not have worked? It might have got overwhelmed, which can happen. Let me just change once. Oh, you know what? My calculator is a little devoid of common sense. No, it's still devoid of common sense, but not because of that. Yeah, it got overwhelmed because it would have to create bars going from 13 to 200 and yeah, so that's like 226 bars. I don't think it's saying I don't have enough room to fit what you want me to fit in. So let me give you a streamlined version of it. So let's say the one at 145, there was no mode at 145. I still want to show you how to do it. So 13 to, let's say, I'll even go 20 to 50. 20 to 60, I mean. All right. So just in this frame here, if I hit trace, each entry, you see, is basically a bar of a histogram. Some have height of 0. A lot of them have height of 0. This is 20. 20 to less than 21 is saying 20 and all the decimal values after 20. So 20, 20.25, 20.28, whatever. Right? So keep hitting the right arrow until you get something that occurs more frequently than anything else. Right? So these occur once. Basically anything that's got a high bar. You're looking for the highest bar. I have a high bar at 45 and then another high bar at 55. All right. And you see how skinny those bars are. That's why it couldn't handle the 145, because it couldn't draw bars, physically draw bars. Because this is how thick it has to make them and fit the interval from 2 to 100 and whatever it was, or 206 on the same screen. So that's why it failed. But on the reason I took the time to go over this is because on the test, I'm not giving you that much data over that wide of an interval. So this technique could work based on what I'm going to give you. All right, the mid-range. I mentioned this when we went over it the first time, and I'll mention it again. The number one mistake on unit test number 1 in all the years I've been doing this, 18 years. It's gotten better over the years, but it still is the most frequent mistake compared to anything else. This is the mode of mistakes. All right. So, and it's because people think mistakenly, when they don't know, they're panicked. I should have studied that. I wish I studied that. They think, okay, well, the range is 193. The mid-range is probably just half of that, so chop it in half. Well, if it were that easy, it wouldn't exist. All right. If it's just take a number and chop it in half, why even ask the question? All right. So what it is, in fact, is the average of the min and max. So you're taking the same 2 ingredients, but you're doing something different with them. All right, so I'm taking 13, adding 2 at 206, and then dividing by 2. So it's 219 over 6, so what is that, 159.5? No, that would be 30. Yeah, 109.5. But you have calculators, so obviously don't leave it to chance. All right. So I put a star on that one. You should put a star on that one. You should, and I hopefully mentioned this. I try to put it in your calendar. Set an alarm for next Saturday morning. I don't know, whatever it is to remind yourself at the last minute. If this is something you think you're going to forget, put it on your 1 3-inch by 5-inch note card. I don't require that you put any information, any particular information on that note card. It's all for you. You put whatever you want on there. You want to put one folder, you look at this entire review and you say, all right, I get everything. I don't know how to do empirical rules. So I want to take one side of my note card and put a complete solution to an empirical rule question on there. Be my guest. All right. I wouldn't do that personally, but that's for you. All right. Question?
Leave it at 109.5. No rounding, right?
No rounding unless you're told otherwise in the question. All right. Variance. So variance, maybe that's something you're in or worried that you might forget. That is the standard deviation squared. Using calculator jargon, that's SX squared. All right. We want the most exact form. It is entirely possible that you can take some rounded version of this number, possibly what we wrote down here for standard deviation, square it, and get the right answer when rounded, but not guaranteed. It might introduce an unacceptable amount of variation. If it does, you lose credit. Okay? Not full credit, but some credit. You don't want to be in that position. So you're going to do one of two things. You're either going to retype this entire decimal and then square it, or you're going to use the standard deviation function that's built into the bars menu. All right, so after we ran that calculation, anytime I would hit SX, it would come up with that number. So I would hit vars, go to statistics, option 5, select item 3. Vars is right next to clear. Then I believe option 5 is statistics. And then you want option 3. All right, that'll put that in our home screen. So this is vars stats, and we want me. All right, so once we select that, option 3, hit the power of 2, which is right next to the comma, the dedicated power of 2 button. You don't need to use the caret key. And then hit enter. All right, if you want to verify it, you can, I mean, you're taking a test, so why not? 51.15557128. Do it a different way, make sure you get the same answer. And, you know, just for giggles, I'll do the rounded form and see what the difference is. For rounding to 3 decimal places, we're going to get a different decimal value here, 0.892 as opposed to 0.936. Now, if you're allowed to round to the nearest tenth, which you won't be, but if you were allowed to do that, then you'd get something that is equivalent. But unnecessary amount of variation, that would be a problem. We don't want that. But definitely worth doing it more than one way just to make sure you did it right. That's just, I think, math sense. 2616.892 is what we want. Right? Snotty comment of the day. If you don't like any of this stuff on the calculator, you're more than welcome to do this all by hand. That was more of a joke than anything else, because I don't think anybody was seriously entertaining finding standard deviation by hand, all right, especially for that mega list of data. All right. So hope. What's that? 7 hours. No, I give generally 2 hours for a test. All right, so that give anybody who gets the extended time as an accommodation through Disability Center would get 3 hours. So 2 for non-disability services, 3 for everyone else, or 3 for the disability services.
By the way, my 11-year-old has a question. If you use with me, she loves your class. She understands everything.
All right. Okay. Now, did you hit the thumbs up icon at the bottom?
She actually, she's allowed, like, I don't know, different username.
She's more than. Oh, comments are welcome as long as they're positive, of course. Yeah. I mean, if people say things like constructive criticism, all I hear is criticism. So I only like nice things. I think, yeah, nice things in writing, or nice things as a posting, negative things as like a remind message or an email. Like that video, it was like, it wasn't that good, it was grainy or something like that. Send that as a separate message. Don't embarrass me in front of the universe. It hurts my feelings. I get all emotional. All right, so empirical rule. That's our favorite one. So you know enough now to know that that's not your favorite one. All right. Empirical rule to determine if the data for 2005 follow. I'm sure that's grammatically incorrect. So somebody take care of that if you would. X bar plus or minus 1s needs to be within 68, or it needs to capture 68%, approximately 68% of the data. We start with that one because if it fails that one, it's going to fail the other 2 conditions, which is good as a problem on a test from a student perspective because it means less work. All right. So what we're going to do is take our mean of 47.968 and do plus or minus 1 times whatever our standard deviation is, 44.393. Let's look at that in the calculator. This probably not necessary for now, so I'm going to hide it and minimize. All right, and also for the next question, remember we do have this baby here, so that'll be fun. All right, so 47.968 minus 1 times 44.393. All right, you could use the var stat stuff, but for this kind of question, rounded values are fine. So we don't need the most exact form because we're going to be only looking for whole numbers in those intervals anyway. So run the first calculation starting with the minus. Then hit enter. That'll give us our low bound, 3.575, barring any mistakes. Then second enter to bring back the last calculation. Change the minus to a plus so that we get the upper bound. 92.361. All right, so that's our interval for 1 standard deviation about the mean. This particular review problem set is a little annoying because of the again the length of the data. So what we have to do, if you remember from the lesson on this, is we now have to figure out how many values fall in that interval, right? So 3.5 is obviously between 3 and 4, and this 92.3 is obviously between 92 and 93. So what I need are values that are between, because they're all whole numbers, between 4 and 92. So count between 4 and 92, inclusive. All right. So, wait, 2005, right? All right. So we want to know, is this approximately 68%? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25 values. All right, so 25 values. If you get something different, let me know. All right, there are a total of 31 values. So 25 out of 31. About 81%. This is nowhere near 68%. Therefore, empirical rule fails. And it's not a normal distribution. And that's like the best possible news. All right? Because if it passed, if you got anything between 66 and 70 inclusive, then that means you'd have to move on to x bar plus or minus 2s to see how many values fell in that interval, and whether or not that was close to 95% of the overall data set. And then you'd have to move on to x bar plus or minus 3s to see if you were close to 99.7%. Obviously, from a test taker student standpoint, with an eye on actually finishing the test, this is good news. It means you're done with the problem. Although you do want to have a nice, quick, easy way of checking your work to make sure that you didn't make a miscalculation, because you don't want to. I mean, it's nice to be off the hook to not have to do the extra work, but you want to make sure that you're correct in not doing the extra work. So one way to do that would be to just take a very quick look at the box plot. Maybe even do that before you get started to see what you're up against. So my data, again, is in L2, because it's 2005. So I would just do second y equals, hit enter on plot 1, change it to a box plot, ordinary box plot. Again, my alpha lock is on. I have no idea why. I'll investigate that later. And then change it to L2, and then hit zoom 9. So create the box plot. That doesn't look normal at all. And you know, the statistical term normal, because again, statistics, where we don't care about your opinion. So it's like, yeah, it doesn't look normal as in what a box plot would normally look like, but that's not what I mean. It doesn't look like a symmetric distribution with the box occupying the bulk of the data, 68%. You know, it's skewed in some capacity.
Just explain one more time what you have the 68%.
That's the rule. if you look at your notes under empirical rule, the percentages are given at 68, 95, 99.7.
Oh, okay.
Recommendation. If it's not something that you think you're going to remember, get it on the note card. Empirical rule, 68, 95, 99.7. Throw an approximate symbol in there to remind yourself that they're not exact values, that you have some wiggle room. You know, maybe make a note that plus or minus 2% is what we mean by approximate in that context. Right? Little things. What's that? 99.7, yeah? Look for symmetry first. If it's not symmetrical, it's never going to be normal. All right. If it turned out it was symmetrical, so if the box were in the middle, you'd also need the median line to be in the middle. And also it should occupy, I mean, how can we judge what 68% really looks like? But it should look like the majority of this number line here is covered by the box. So something like this. All right. If you have that, then you're looking at something that's probably normal. Not guaranteed. That's why we do the empirical rule to begin with. But at least you know it's worth your time to do the empirical rule. You know that it could potentially give you a yes. That graph tells me it's going to be no. But it also is very satisfying because going into the problem, it's like, all right, I'm going to be done with this one real quick because all I have to do is one calculation to justify it. All right. Number 5. Determine any outliers and unusual values for each data set. Justify your answer. All right, very important. So apparently I start off every question by saying very important. I notice things like that sometimes. Two different rules for outliers and unusual. Outlier formula. LQ minus 1.5 the IQR, comma, UQ plus 1.5 the IQR. Very intimidating formula, but we have two nice workarounds. Two very nice workarounds. We'll get to those in a minute. X bar minus 2s, comma, X bar plus 2s. That's going to help us determine unusual values. All right. So the one thing to remember is anything that falls in this interval is non-outlier, is a non-outlier. And this is not unusual. Outside of those intervals would be where you get your outliers and unusual values. All right, try to give something for everybody. But the outlier approach, if you find yourself using this formula on the test, you've already failed. No, it's not really not that bad, but it's you're probably allocating your resources the wrong way. So let's focus on outliers for a second. We got 1970 and 2005. This is kind of misleading. Justify your answer. I don't need an essay. I don't need a complex algebraic approach. I just need you to tell me what you did to get your answer. All right? If you use the calculator approach, tell me what you did on the calculator. All right? And I don't mean keystrokes. I hit this, then that. Just give me an overall sense of what you did on the calculator. That's all I need for work. Answer, overall sense of how you went about getting that answer. So let me get into that. So 1970, I'm going to create a modified box plot. So second y equals, to get us into the plot, stat plot editor, I want plot 1, I want to turn that on. It's been on, so it's really just a matter of toggling what type of on. Down, and select the one that's not the ordinary box plot, the one with the 2 little dots. We know by now that those 2 little dots are outliers. Right? If they show up in that graph, then they're outliers. If they don't, they're not. I want to look at L1 first. So my alpha's on again, so I'm going to hit second one. And then just a quick zoom 9. Let me snip this in here, though. I'll just kind of tuck it in over here somewhere. Because we have a program, but I think most people are going to want to do it this way if they go to the calculator route. So zoom followed by 9. All right. So the question is always going to be, what does this tell us? And I'm going to say that there are no outliers. And that's because the modified box plot has no loose points. All right, if you want to provide a quick sketch, calculator gave you the box plot. I mean, how hard would it be to just draw a quick sketch of the box plot and write this explanation? You don't even have to get into what you did in the calculator at that point. It's implied, you know? Or you can say, I created, there's no outliers. I looked at the modified box plot on my graphing calculator.
So we do the diagram. How do you know there's no outliers?
There'd have to be a couple of disconnected points in this graph somewhere. All right, so maybe there will be for 2005, so let's take a look at that. So we do the same thing again selecting this graph, this time for 2005, so that's L2. Zoom 9, no loose points, no outliers. Now, when you're taking a test, you don't really have any kind of rooting interest. You just want to get the problem done. But if there was ever a case where you want to have some rooting interest, it might be this scenario. You're talking about infant mortality rate. The lower, the better, right? So if I had a data point like a country in a particular year, and they ended up being an outlier on the low end, that would be really good for that country. It's like, whoa, what are you doing right? Let's see if we can do what you're doing. Right? What you would also not want to be, like contextually, is oblivious to the fact that outliers in the other direction would be terrible. So if you have a list of all the countries, but a couple of them are outliers on the high side, that means their infant mortality rates are so high that they're standing out in the data set as being something that's borderline impossible. Like, it's so high that this can't be happening, it must be a mistake. Then you look at it and say, whoa, it's not a mistake. And then you have that sinking feeling of like, what the hell is going on over there? So, I'll go with something a little gentler on the test because I don't want to put people in a funk, but on a review I don't have a problem. But yeah, that kind of context, you really want to think about what it means. The analogy for me is always golf scores versus basketball scores. Golf, you want to have lowest possible score that equals the best performance. Basketball, obviously, the more the better. All right. Now, unusual. These are typical values, but you didn't see them coming.
you just show us like on say where like a point would be that would be an outlier?
Sure. So let me modify the data set to create an outlier. So I just got to remember that I changed 2 to 2,000. Obviously, an increase of 2,000 per 1,000 live births doesn't make sense, but we'll go with it anyway. All right, so you have this loose point over here. No problem. Let me change it back and forth again. Okay, so for the unusuals, we just have to do the x bar plus or minus 2s. Again, for each year, so that's mildly entertaining. I need my information for 2005. So 47.968 minus standard deviation for that year was 44.393. 2 times 44.393. All right. And then we also have to find the upper bound for that, which would be the same stuff just with a plus sign. Clone. So I'm just going to kind of stagger it this way. So 47.968 minus 2 times 44.393. Enter. Second enter to recall the previous calculation. One of the more useful steps in the calculator. TI-84s, you could just hit the up arrow, but even with TI-84s, I still like hitting second enter. If you want to go back 2 or 3 steps in the process, like 3 calculations ago, just hit second enter, second enter, second enter. All right, so keep performing that calculation or those movements, and you'll be good. All right, so these are my particulars. A little cut off, but we can live with it. All right. So this is the set of usual suspects. For 2005. I wrote 1970, but I pulled the information from 2005, so sorry about that. So a little backwards. A little late. All right, so our interval for usual values would be anything between negative 40.818, which, you know, negative values wouldn't make sense in this context unless you're talking about like 40 per 1,000 immaculate conceptions or something like that. I don't know. So in 2005, we're looking for anything. So low end, we're not worried about. On the high end, we're looking at anything more than 137 or 135, 136. Let's split the difference there. 0.7 or 8, something like that. So that wrong way, like the calendar issue. So got 2 of them, right? So they're not outliers, but they're definitely high enough to be considered unusual. Kind of look at unusual as being cause for concern. outliers is being cause for alarm. It's more extreme. Or if the unusual is alarming, then like outliers would be a scale above that or a level above that, like a nuclear holocaust, something like that. Something just dreadful. 197. Okay, so I will now use a technique I like to call the right way to come up with 1970. So we have 90.323 minus 2 times 51.156 and then the same stuff again, but with a plus sign. Smidge it down a little bit. All right, so second enter to get the previous calculation, go back, change minus to a plus. We have our interval. You don't have to count anything in terms of the number of values that fall in the intervals. We just need to know which value fall outside the intervals, not in the intervals. All right, so state the interval. Again, I don't care how you come up with the interval, short of cheating, of course. It's one of those things because whether you realize it or not during a test, I'm watching even when it looks like I'm not watching. I'm always watching. Sometimes I'm watching through my phone, which is really diabolical on my end, but I caught a couple people cheating that way once. So it's really kind of mean. But what I do is I have my video feature on, and I'll look like I'm just texting or something like that, but I'm actually just watching everyone. So I'm not recording though, I promise you, but I am watching. Right? So yeah, I busted somebody. Oh, and fun fact, he was the student trustee for the college. Yeah, busted cheating. So so yeah, even the most honorable. Anyway, honorable. So the reason I do stuff like that is so that you can write just this down without showing me all that crap that came before, right? Because the only reason I think any math teacher ever requires you to show work is to prove that you weren't cheating. Because in reality, it would be so much more convenient for us if you could just write the answer down and move on, right? This is one of those cases where if you come up with this interval and you didn't copy off someone else, how else would you have come up with that interval unless you knew what you were doing? So, good. Keep doing what you're doing, short of cheating. So, anything north of 192 would be considered unusual. All right, so definitely a little morbid for a Saturday morning, but definitely really talks about the importance of statistical analysis. You know, some of us are taking the course to check the box, but some of us are taking this to see if we can actually use it in real life. This is an example of how you might go about using something statistical in a real life context. It's pretty cool. I mean, not the results, but the process, obviously. The results